Okay, welcome everyone. It's Graham Smith here from UNIGIS UK. I'm based at Manchester Metropolitan University. Thanks very much to everyone for taking their time out to attend today's webinar. And this is the first of the spring series of UNIGIS U lectures that we'll be hosting. So please look out. There's several to follow, and you can access details of them from our website. So thanks very much to today's presenter, Rachael Reynolds. Rachael is a PhD student here at Manchester Metropolitan University, and Rachael's now in her second year of her PhD. She actually has a first degree in geography from Manchester Metropolitan University as well. And Rachael is working on a PhD with Mark Creswell and Gina Cavan, based both here at MMU, or Manchester Metropolitan University, and obviously our tutors on the UNIGIS programme as well. So Rachael's PhD is based around matters relating to health, climate change, remote sensing and GIS, and really what I'll do is I'll hand it over to Rachael now, who can explain all this in a lot more detail. So I'll just click over to change the presenter. And hopefully you'll be able to see Rachael's presentation. And if you can still hear me, the last thing for me to say is that if you've got any questions, please post them using the question forum. Over to you, Rachael. Thanks very much.
Thank you, Graham. Hello, everyone. As Graham mentioned, I'm Rachael Reynolds, and I will not go into that any further. I will let this presentation do the talking about my work. So I am studying climate, environment and disease in Tanzania. Just to give you a very broad overview of what my PhD is. And in this presentation, we're going to be looking at a number of things to do that form the basis of my research. So I'll introduce you to Tanzania for those of you who aren't familiar with the country itself and why Tanzania is such a good country to study, particularly for climate and health. Before moving on to the earlier stages of my research and why there is a gap here and what needs to be done and can be done for this, before giving you the preliminary results or an indication of what can be expected from these results, before going into future work, and also why this is a very important matter that needs to be studied in considerable detail. So to begin with, Tanzania, as many of you may know, is in Africa, on the east coast. It has quite a large population. These are the most recent estimations on the screen now. But as far as countries go, its population density is quite sparse. We have areas of a lot of people coming together in one place, such as the coastal city of Dar es Salaam, as well as Dodoma, which is the recognised capital. But there are also a lot of outer rural communities as well, which makes it a very interesting country to study for health, because the records can be very sparse. In the built-up areas we have very good records, but in these rural areas it's a bit hit and miss. It can vary. When it comes to the climate of Tanzania, it's largely tropical, but its topography gives it a very interesting range. As you can see, their elevation ranges from 0 at sea level, peaking at Kilimanjaro at 5,895 meters above sea level. So that gives a lot, quite considerable amounts of height, which is crucial to vectors, which you may or may not know is what transmits malaria. It's fair to say that this is quite a prevalent disease in the world. Many people know of it and of its capabilities in terms of death. But what is also a crucial factor in this is malaria is also preventable. I will go into, malaria isn't the only disease that is covered under this PhD. There are other diseases which I will go into. But we'll start with looking at the climate. Broadly speaking, Tanzania can be broken down into 7 or 8 climatological zones. This is a source from the Tanzania Meteorological Agency. And these are all based on different rainfall patterns, different temperatures, and a lot of it is also correlated to the topography, as I'll show you in the next slide. One of the biggest factors, particularly for African climate as a whole, is the reliance upon rainfall. As you may have seen in the previous slide, agriculture is a big foundation of job sources and thus what people spend their time doing and what they need the climate for in that respect in terms of economy. And the intertropical convergence zone, as shown in the image on the right, is a provider of this. This is what controls that movement of rain across Africa. I'm not sure, it's not very clearly depicted on this image, but as you can see on the eastern coast, how best to describe it is that Tanzania is covered by multiple bands, as it were, where we see in some areas rainfall from May to November, some areas March, December, some of them have twin rains. This is typically categorized by the north of Tanzania experiencing the bimodal rainfall period, as it were, where the tropical convergence zone moves down across it and then it experiences as it's moving back up across it, whereas the south experiences that unimodal rainfall regime, where that is the sort of peak extent that the intertropical convergence zone moves downwards. So this gives a very different climatological landscape, as you can imagine, with some areas experiencing 2 rainfalls and working around this, and one area experiencing the sort of unimodal rainfall. And this shapes lives considerably, and also not just people's lives, but the vectors' lives which carry these diseases. You can see that sort of translates over to that climatological zone. You can see that there are very clear splits, particularly along, if you look along that central, down into the north central there is that sort of slant. It's not just defined by rainfall. Obviously temperature is a key factor, and with it being very close to the equator, you get quite significant extremes where it can range from getting quite hot during the day to dropping considerably low at night, which is again shaped by the topography. So we'll start bringing this now. This is a digital elevation model of Tanzania. As you can see, the coastline remains very, very low. It's very flat. Generally, you'd expect it to be warmer around here. We have some of the air being kept down by the proximity to the ocean before rising and generally cooling as it goes up in elevation. Tanzania is defined by a central plateau, which it is quite well known for. You have, as you can see to the northwest here, it seems to be fairly consistent before you get to these mountainous areas. So we have the northern highlands and the northeastern rift going along here, and this is generally where Kilimanjaro would be found as well. You can see it just there at the top. Kilimanjaro is, as stated, the highest peak in Tanzania. So this is quite an interesting place to begin with, let alone the highlands themselves and how they split Tanzania, that very clear barrier between the sort of level plateau and then that low-lying coastal area. This creates, if you consider the intertropical convergence zone as well as temperature, it has the potential to create very, very different landscapes, which it does. In turn, this provides very different environments for diseases to thrive in. So as I mentioned, there are diseases, bringing diseases into this. They are considerably affected by climate, some more than others. Some diseases are not influenced by climate at all. These three presented here are an example of diseases which either have been present in Tanzania, are currently present in Tanzania, and some which are growing. There are several studies to suggest that malaria is one of the growing diseases. It's quite thoroughly studied in comparison to bacterial meningitis and chikungunya. And this trend has started to be seen in terms of creeping up in elevation. So as the climate is perceived to be warming, we're seeing that this temperature range which the malarial mosquitoes can survive in is starting to increase in altitude, which is quite concerning. As you can see, that malaria is transmitted by this parasite, by the vector. It's a parasite which is transmitted by the following vectors, the Anopheles gambiae, Anopheles arabiensis and Aedes aegypti, and each of these three vectors are capable of surviving in different environments. So for example, Aedes aegypti is very commonly known as the domestic mosquito, as it were, the urban mosquito. It's found in very built up environments. It thrives it can thrive in very small, shallow pools of water. It rests indoors as well, meaning that anybody going to sleep at night leaves themselves open if they don't have a protective net to being bitten by one of these mosquitoes. The other two generally found in either perhaps more wooded areas or more open rural areas, which pretty much covers a significant amount of Tanzania. Bacterial meningitis is considerably different to malaria in the fact that it is a bacteria of which there are several serogroups present in Tanzania. One of the serogroups, I can't remember this off the top of my head, I'm afraid, but it is now able to be treated quite successfully. What a number of studies have shown is that this has begun to change, whereas this serogroup is being able to be combated, another one is taking its place, which is of considerable concern. This one is transmitted via the air. Humidity is a considerable factor in this, and the original bacterial meningitis belt, which spread across the Sahara, has since been redrawn since it was first conceived, and now spreads down into the northern parts of Tanzania as the conditions have changed that much that now it's suited there as well. Chikungunya is the chikungunya virus, which is why it's not named under type there, because it is the chikungunya. Also spread by Aedes aegypti, so as you can see there is a crossover there in vector transmitters, meaning that where you find malaria you could also find chikungunya, potentially, given if the conditions are right. But each of these, let alone the vectors having their own specific conditions, each of the parasites and virus and bacterial limits have their conditions as well. Chikungunya, I believe, is a virus that it will perish upon reaching 52 degrees, but obviously anything below that is fine, and we do not see that sort of temperature anywhere really, let alone Tanzania. So that is of considerable concern. Whilst they do have their perish points, they are considerably extreme and robust. They can survive in quite intense conditions. The symptoms of each of these diseases can often be mistaken for other factors as well, which is something to be concerned about. That's more towards the end of my PhD, when we're starting to bring out the predictive model and seeing how that could impact on potentially providing real world solutions. So the big connection between climate and health is this relationship between the climate, temperature, rainfall, humidity, how this is changing the environment in the fact that a mosquito, as you can see on the left, needs water to be able to reproduce. And to support this, temperatures of certain conditions are also needed. So we look at these in terms of degree days, whereby the temperature is somewhat consistent over an X period of time to allow the full growth cycle to be completed. So it's got to be within a certain range. Sometimes if the temperature is lower, it can take longer, and if it's higher, it can take quicker. On average, I believe it can range from a week at most optimum temperatures where conditions are perfect. There's enough water, there's enough shade from vegetation, which is quite an important factor because many mosquitoes do perish in particularly high heats as adults, let alone as the more sensitive larvae and pupae stages. And then the temperatures to allow and control that reproductive process. Obviously, the quicker that a mosquito can grow and get out, the sooner it can lay eggs, the sooner that process continues and that mosquito population can expand. So this is where climate and health is linked in the respect to the vector transmitted diseases. Obviously these have stages within them of their own as well. The parasite and the virus both need certain incubation periods as well, controlled by bodily temperature and also temperature within the mosquito. As I said, mosquitoes perish if they're out in the sun too long. They get too hot. This is the same with the parasite as well. If the mosquito's body temperature raises too high, as it's not doing so well out in the sun, the parasite with it can also perish. So this is added complications to this cycle. As you can see on the right, this is it within the human. It's showing the sort of development stages within the mosquito itself, which is where it's incubated and it grows into the parasite, which can cause damage to the human body, and it can be, as we know, fatal. It's a similar occurrence with the virus. It's less complicated with the virus, but it does need to be kept at a certain temperature. For bacterial meningitis, it's the more external factors that we're interested in terms of climate and health there, because that's the outside conditions which allow for those dusty, humid, dry, that atmospheric condition to allow that to be spread so easily through close human contact in that airborne manner. So why is this of a growing concern, as it were? So looking at vector distribution in relation to the climate, as I've already mentioned, there's a change in that distribution and frequency of epidemics. So they're rising, mosquitoes are rising in altitude into areas that they were not previously known or experienced, something which I've experienced firsthand as I've been out to Tanzania, went to a college up Kilimanjaro and spoke to some of the people there. They've been living there for a considerable amount of time, some of them 40 plus years. And in that time, they had noticed just by themselves increasing incidences of malaria, growing populations. One of them very explicitly said to me that we didn't used to get mosquitoes here. They weren't there. It wasn't capable for them to survive. So the studies correlate with what the people are saying. It's all sort of coming together now, and it's something which has become very commonplace there. They seem to have accepted the fact that mosquitoes are now very comfortable there. One thing that has been highlighted is that potential alignment with the El Niño Southern Oscillation, something which I will go into a bit more detail on a bit further on. The gap which this PhD is starting to address is that it remains unclear the exact role and relationship that climate change has played. We know that there is a connection. We know that by temperature change, this can change evaporation rates of water, thus impacting on water levels, which is requirement for the mosquitoes, and also vegetation cover as well is quite important in a mosquito's habitat for survival, for its own survival. What's also remaining unclear, particularly in Tanzania, which is classed as a less economically developed country where its roots are based in agriculture and mining, a very much outdoor job which leaves them open to encountering more mosquitoes, as well as the obvious indoor mosquitoes affecting the urban environment, is the changes in relation to these jobs, the movement of people, with more people gradually becoming more educated, going to the city to pursue better jobs. How is this affecting it? Are they taking these parasites with them? An individual could be infected for a few days before even knowing that they're infected with a malarial parasite. And also access to healthcare is quite a big one. Tanzania has made quite a push forward in getting better healthcare countrywide. They have a system similar to the one in England, the national health system. However, this does remain very sparse, particularly in rural areas where there are shortages of supplies. Again, I met with health professionals out there, and it is difficult to get the required drugs and supplies to the areas which need it the most in some cases. Further to this, as you can see, there's all sorts of drug resistance and control activities which play a factor, and these are all things which will need to be considered in the final stages of my PhD, but for this particular presentation we'll be looking at the climate and getting that disease risk mapping element into it. One of the first things that I looked at was doing a basic disease map, a risk map. It's quite common practice. It's found in a number of journal articles as a good foundation to build a study upon. So data for vegetation elevation and the total precipitation and mean monthly temperatures were collected from MIDAS stations from June 2003, and June 2015. Before I carry on for this slide, I'm going to come back to it in just a second, but I'm going to show the visual difference. So ENSO is the sea surface temperature anomaly, where we have unusually, so in an El Nino year we have unusually warm sea surface temperatures, as you can see there in figure 3b. As I mentioned before, El Nino can have a significant effect on disease. It changes conditions quite dramatically, particularly in Tanzania, to allow for warmer conditions than that more optimum temperature, and also provides altered rainfall patterns. Theoretically, a number of studies do show that. There are numerous studies out there which have looked at this from various angles. But this is what it looks like from the satellite. This is from NOAA. This is sea surface temperature, as you can see, stemming there off the coast of Peru. It's very clear, very, very clear warming trend, and this is picked up by teleconnections in the atmosphere. The heat rises into the atmosphere and it does impact it across the globe. 2003 was chosen as a non-El Nino year, so this is as close to average conditions as we will call it, as was possible. when I was looking at this. So as you can see, it's still fairly warm. We have patches of warmth, but we also have quite a fairly cool, and it's not direct. La Nina you'd see more like an El Nino where it's very, very direct cooling. It'd be noticeably colder, that direct line, whereas this, it's got interspersed with little bits of warmth here and there. It's still just churning away. So that's why these years were chosen, with that stark contrast. The values in the table to the right were all chosen for the justification reason given. I won't go into that on too much detail. It's there for you to read, but it's all to do with that mosquito survival and breeding. So if it favoured the mosquito, I assigned it, if the conditions that were there favoured the mosquito, I assigned it a weighting of 1. It's suitable for the mosquito, it's suitable for the disease. That's, 1 is the correct indicator to give it, but if it was not suitable, then 0. Based on these 4 parameters, the results were combined, and this first one I'm going to show you is the total area of change. So for each of the 4 categories, if it was assigned 1 for each category, meaning it would be the highest risk of disease, every suitable condition was met, it'd be a category 4. If 3 categories were met but 1 wasn't, it'd be a category 3, and so on and so forth. And the map of, so Tanzania was laid out in a GIS. It was mapped over, all of these elements were placed over and calculated. And the change between June 2003 and 2015 it is quite significant. I mean, on first glance, it might not look at it. We see a 1% in total kilometres squared of area covered. Yes, a minus 0.86% decrease. So for a country that's particularly big, that is quite a large area that has changed. So it's decreased for category 2, which on glance would say it's a good thing, but as we can see, more areas have now spread by just over a 1% increase in category 3, meaning that those areas which were once category 2 have now moved up. For 2015, the risk category for catching a vector-borne disease grew quite significantly. Otherwise, we can see 4 also decreased a little bit, so some areas were less prone or were less at risk of getting a disease. These are the actual output maps themselves. This is why I put the bar chart in, because it displayed it more explicitly. The shading on these maps perhaps doesn't lend quite so well to showing that, but as we can see between 4A and 4B, where 4A was for 2003 and 4B for 2015, we can see that overall the map is considerably darker. Those areas are now at a higher risk, but 4C really picks out those places which have increased quite significantly. Along the coastline seems to have, if you notice, it seems to have not very little change at all. This is an area that's already quite low and quite used to, well, experiences, mosquitoes are very well established there. Whereas if you think back to that digital elevation map, those mountainous areas have started to depict in this one. You can see that category increase, particularly places around. This is why I've put Sumbawanga on. Dodoma, which is the capital, appears to not have that much, but if you go to the south of that, there is quite a large area of change here. And similarly, around the lakes where Mwanza is, you have quite a significant amount of change, suggesting that the disease risk does go in hand with an ENSO event, in turn meaning that the climate has changed in some form. in this case normally increasing temperatures and also increasing amounts of rainfall as well. The second part of what I've done so far has been looking at the areas of climate sensitivity. So following on from that, I've picked out areas of potential where the disease risk could increase, often around the mountainous areas. Now I'm focusing in on some of these areas. As you've seen, ENSO events are useful to highlight of those areas sensitive to disease risk and thus suggesting climatic change. I've used the MIDAS data set to be able to create a baseline climatology. Most climatologies are able to go back, well, an ideal one would be 30 years, but this one is only able to be 10 years, just down to the fact that data coverage in Africa is not that good in comparison to the rest of the world. It's just less invested in these less developed countries don't have the means to be able to sustain this recording of climatic data, really. But this is increasing due to work like the UK Met Office is now doing with the Tanzania Meteorological Agency and has been doing with the Kenyan one as well. They're trying to increase that data availability. With this one though, I've started to look at how two categorically strong ENSO years, so 1997 and 2015, compare to each other as well as the baseline climatology. So I'm looking at how they all differ from the baseline climatology or the average climate of Tanzania, and how they also differ from each other. Is Tanzania experiencing the same sort of change with each ENSO event, or do those in turn themselves differ? Kilimanjaro was chosen to be the first station examined, so it's the one that I presented here, given its interest, altitude, and this is the recording station at Kilimanjaro, or one of them. This is one that's a little bit further up the mountain at the college that I went to when I visited. Now, these are some of the preliminary output, so you can ignore the numbers on the side unless you are interested in them, in which case by all means have a look. But starting from the left with the baseline climate, years 1985 to 95, you can see a fairly steady temperature. It's, you know, the histogram for this one is fairly consistent, though there seems to be no major extremes, as it were, none out of the ordinary. It seems to follow that that good shape. But if we're looking at 97, for example, it demonstrates a very, very different pattern of air temperature. It's much more sporadic in its distribution. And furthermore, if we're comparing this to 2015 as well, it's got a very, very different pattern. This suggests that even though they are the same category as far as ENSO events are concerned, as categorized by NOAA, their impacts are significantly different, which is quite interesting in itself. When moving on to rainfall, as you can see, this one stands out quite significantly. When it comes to the baseline rainfall, it doesn't generally increase, sorry, let's just say 2 millimeters of rain, and it generally stays fairly flat. We have those, you can see some of that by bimodal trend that Kilimanjaro experiences, with it being in the north of Tanzania, where it increases from October, November, December. It begins in October, marks month 10 on the graph, before continuing into the stronger rains in March, April and May. Whereas 2015 and 1997 demonstrate significant increases in rainfall and not necessarily in line with what is classified as the standard rainfall period. There's quite a large increase in rainfall in April for 2015, whereas this seems to have been delayed a month to May in 1997. If you look at this overall as an abstract, you generally think that rainfall could potentially have increased by a similar amount. This is still something that I'm writing up at the moment, which will hopefully be coming out later this year. And so I can't confirm the exact values for you at the moment, but on abstract you'd say that it potentially has increased by a similar amount between these years. But what is noticeable is also the distribution, and what needs to be done is this needs to be compared to the temperatures to examine that evaporation rate and thus impacting upon the mosquitoes' habitat and potential breeding sites that this may bring about, this increase in rainfall. This will then stay around perhaps for significantly longer than it otherwise might do, potentially going into months where you'd see no rainfall, but you still have mosquitoes breeding due to the sheer amounts of water that it would be available on the ground or collected in pools within urban environments. So the summary of the implications of this research so far is, firstly we'll look at the disease risk mapping. It suggests that disease risk countrywide could potentially increase, particularly in mountainous areas where that altitude change comes in, where areas which would not have previously experienced disease in that way due to the altitude now could potentially do, and this exposes populations which have no natural herd immunity to diseases such as malaria and chikungunya, which allows also for a faster spread rate. This is further supported by the literature and supports the literature in itself. And as I mentioned, for the coastal areas, there's little change seen there. This is already a high transmission area, so there is not much change seen there. Kilimanjaro's sensitivity to El Nino events, it does demonstrate a considerable amount of sensitivity given the increase in the increase in rainfall in certain very particular months, it appears to be so far, and also that change in temperature, which appears to be very sporadic, with 97 having consistently lower temperatures than the baseline and 2015 demonstrating higher than average temperatures. So that could swing either way. There isn't a clear outset there for how ENSO is affecting that particular place, Kilimanjaro, for that. Overall, this has the potential to increase the breeding habitat, extending the breeding seasons, exposing more populations to malaria, chikungunya, for example, as the vectors are the ones which have been focused on in this particular study. It leaves a lot of questions to be answered in that respect. So the further work of where this is leading to at the moment is to further quantify. At the moment I'm in the stages of quantifying those changes, ready for further presentation at conferences, and beyond this I'm now starting to bring in the impact that those climate and rainfall changes are having on the local vegetation, in this case a mosquito's local environment. They need vegetation to survive during the day, and larger bodies of water such as the Lake Victoria, which extends into Tanzania. These large bodies of water can sustain on the edges. They sustain many, many villages as well as mosquito populations. They provide reeded shelter and adequate water for them to breed. So this brings people and mosquitoes together in areas which have perhaps less access to healthcare facilities. Also with this, considering that ENSO is a sea-based phenomenon, it's crucial to perhaps look at the potential advanced warning system of the sea surface temperature and how this may be indicated in Tanzania's local sea surface temperature. Just off the coast of Dar es Salaam, there are currents flowing under the sea which could be carrying some of this warm water which is evaporating right off the coast to allow this rainfall, this very, very heavy rainfall during an ENSO event to occur. So this is where the work is starting to go now, with eventually an aim to pick out key correlations between these factors whilst cross-examining some key social and economic impacts, such as the implementation of the programs to help reduce exposure to vectors, so the distribution of insecticide-treated nets and residual spraying, as well as, very importantly now, the job changes, people moving away from agriculture into other forms of work now in Tanzania, but this is still very precedent in rural, so it's getting that rural-urban contrast. We need to really get down to where these diseases are potentially going to hit the hardest, and at the moment that would suggest rural with the added exposure to mosquitoes, given their working hours. As I said, mosquitoes don't like the sun that much in terms of the heat that it provides, so they'll come out at dusk and dawn. So it's continuing to look at all of these factors could tie in as in stages as the work progresses. A good example is the current crisis of Zika, of why this is important. Nobody saw it coming. It was not predicted. It was not a predicted outbreak, but it's considerably grown over the past couple of months. It's a virus spread by Aedes aegypti, one of the mosquitoes found in Tanzania, and it is a growing concern to many populations and has been quite a high impact disease. This just highlights the importance of climate-related diseases, particularly through the vector itself, and why this sort of research should continue, because we don't know how diseases are going to progress in line with climate change. So I've added references onto the end for those. These are all quite recent references for those interested in having a look at those, and also my details if you'd like to get in touch with me or see my photos from Tanzania, from my trip to Tanzania, and my Twitter on there as well. Thank you for listening.
Okay, thanks very much for that, Rachel. I really appreciate it. Basically now going to offer up the floor for questions. If anyone's got any questions that they want to ask Rachel, please post them. I do have a couple of questions in the meantime, if I may. Do you know when you were showing your the disease risk opportunities, you know, in relation to the baseline year and then the El Nino year, they weren't all linear. Why? Do you have any understanding or any reason why they weren't all showing the same response? You had, I think it was at category 2 was decrease, category 3 was a significant increase, and then category 4 was a slight decrease. Is it? Would you expect that to happen because of the nature of the different variables? and they won't all act in a uniform way? Or is that quite surprising that you get this kind of non-linear response?
I guess it's not that surprising that it's been a non-linear response, given the rainfall as a parameter itself is non-linear, and temperature in some cases as well, but rainfall being a key one. It isn't surprising that it's happened in that way. It's surprising, I guess, in where it's happened, and also the amount of land in terms of kilometres squared for that particular example that has been affected by that. So it's not surprising, but it is interesting in where that's happened, if that makes sense.
Yeah, it does. Thanks very much. And yeah, another question actually I've got relates to this sort of the choice of your control site at Kilimanjaro, and obviously the elevation thing, and obviously clearly elevation seems to be quite important. But then I think when you linked to the Zika problem later on in your presentation, that latitudinal changes are increasingly important. So that kind of model of Zika, and given it has the same vector, are you sort of suggesting that what we might see, obviously there's different modes of transmission for Zika they've identified, but might we see some similar patterns with the other sort of health risks that you're identifying and the Zika outbreaks? Might we see the same kind of northerly distribution or higher latitudes coming increasingly into play, or is that that's really, I guess, an aside to the rest of your work, but any opinion would be interesting.
Yeah, no, it's something that a lot of people have asked me about Zika, given that it is a key disease at the moment, and it is something in general in terms of latitudinal change worldwide, as it were. It is something that is of interest. An example from my work is bacterial meningitis, where that has been that latitudinal change across countries, and the same could occur with vectors, definitely, where we're seeing temperature changes sort of begin to happen at higher latitudes. There are cases in Italy now and France where chikungunya has been reported. Recent outbreaks as early as 2009 and continuing publications have increased massively on chikungunya, which is reaching as far up as Italy and France and still growing. So that's a disease that was actually founded in Tanzania in about 1952. It originally stemmed from Tanzania and is now found in Italy and France. So it is potentially latitudinal shifts could definitely be seen. Obviously I'm only focusing on the one country, but it's not to say that this couldn't extend beyond that into other countries and other continents either.
That's great, thanks very much for that. I've got a question from Mark from Manchester, and that's how could knowledge of future risk be useful to people on the ground, particularly in regards to decision making? Any suggestions?
It's obviously model outputs could be very indicative of, for example, if we know that predicted area of increase, say if just using Kilimanjaro as an example, if we know that, say in June, Kilimanjaro's expected to have a significant increase of malaria, but we also know that somewhere such as Dodoma, for example, the capital, is going to not see any change in malaria, or Dar es Salaam, which is on the coast, which sees possibly a more constant level of malaria distribution. We can start to then target resources, medical teams, or even charities such as MSF, I guess, could use this information, saying we know that there's going to be an increase of disease risk here. They could go in there to control an outbreak. They could help control epidemics, so it stops this being an outbreak as serious life-threatening as it could potentially be otherwise without this predictive system. It could potentially save money in terms of resource allocation as well, whereby resources could be sort of wrongly allocated, as it were, to an area which may not experience any change in disease. You've got an area which has used all of its resources and needs the extra because it's now starting to escalate quite quickly. So a predictive model could be incredibly useful in sort of planning on distribution of health resources in terms of drugs and medical workers.
Thank you. One final question for me, and it just relates to the use of technology, and in particular Earth observation technology. You showed some, I think it was satellite-derived temperature data. Are there any new sensors that are planned for the next 5 years or decade or so that you think would be quite important for people working in your area of health and climate research? Is there anything that you're kind of looking forward to particularly be able to get access to?
Yeah, there's the, I know that Jason 3 has recently gone up, and there's Sentinel data as well, which is, I believe it's being rolled out for Europe mostly at the moment, but that is quite good, high resolution data, which is run by ESA. So Sentinel 2 is definitely something to keep an eye on in terms of good quality data that is now being rolled out. I'd say that's probably one of considerable interest to those working in Europe, more than anywhere else at the moment. Africa has always been sort of one of those problematic areas, so it may take a bit longer for that to become accessible. But yeah, I'd say Sentinel is one of interest.
Okay, thanks very much, Rachel. Really appreciate you giving your time today for the presentation. And I'd also like to thank all of the attendees for taking time out of their day to participate. So thanks very much, and that'll be it for this evening's session. So thank you.